In other words, when the angular displacement is 3.14 radians, that's equivalent to 180 degrees. And when the angular displacement is 1 radian, that's equivalent to, well, yeah, work it out, divide 180 by 3.14, and you'll agree that comes out to about 57.3 degrees. So that's what we mean when we talk about radians. If an object moves around a circle and comes all the way back to where it started, then theta is equal to 360 degrees, or about 6.28 radians, or we might say 2 pi radians. We say the circumference of a circle is 2 pi times r. In other words, we're just multiplying the value of the angular displacement times the radius of the circle. So in general, we can apply that same formula to the case of an object that moves any fraction along the perimeter of a circular path. So the path length s is equal to theta times r, no matter what the value of theta is equal to. Now, take note of the units in this case. If we say, if this is the unit circle, then r is equal to 1 meter, and the path length then would equal 1 meter if this angle is 1 radian. But notice what we're saying here. We're saying 1 meter is equal to 1 radian multiplied by 1 meter. That doesn't quite look dimensionally correct. It looks like we have meters on one side of the equation versus radian meters on the other side of the equation. But that's the magic of measuring angle in radians. Radians just disappear out of the equation when we combine them with other units. That doesn't work when we choose degrees as our measurement for angular displacement. It would not be true to say that 1 meter is equal to 57.3 degrees times 1 meter. So we're going to stick to radians as the preferred unit for angular displacement. If instantaneous velocity is defined as dx dt, that's just as good as saying ds dt for objects that move along circular paths. So v is equal to d dt of theta r, right? S equals theta r. No matter where the object is located, if the path really is circular, there's no change in the value of r, there's just an increase in the value of theta as the object moves farther around the circle. So the r is a constant, the theta is a variable, so we can say that v equals r times d theta dt, but that's omega. Omega is d theta dt. So the speed in meters per second for an object that moves along a circle can be found by multiplying the radius of the circle times the angular speed measured in radians per second. Likewise, we define acceleration as dv dt, but we've just found that v is r times omega, and r is a constant, so the acceleration in meters per second squared for something that moves along a circular path should be equal to the radius times d omega dt, but we recognize d omega dt, that's alpha. In other words, acceleration measured in meters per second squared is equal to radius times angular acceleration measured in radians per second squared. Two very important formulas that help us relate linear motion to angular motion. So just one final note on the units of measurement. When it comes to objects that move along circular paths, we prefer to measure displacement in radians, speed in radians per second, and acceleration in radians per second squared. Exactly how fast is a radian per second? So you might be more familiar with RPMs, or better yet, revolutions per minute, as a way of expressing how fast things rotate. Let's try to determine exactly how 1 revolution per minute compares to a radian per second. So we'll do a little dimensional analysis. If we want to convert from revolutions per minute to radians per second, we note that there's 6.28 radians in every revolution. And at the same time, there are 60 seconds in every minute. So if we divide 6.28 by 60, we should have converted into radians per second. And in fact, when you divide 6.28 by 60, you get about 0.105. So a radian per second is quite a bit greater than a revolution per minute. Another way of saying it, if 1 revolution per minute is equal to 0.105 radians per second, then it must be true that 1 radian per second is equal to about 9.55 revolutions per minute. If you spin something around in a circle at exactly 1 RPM, then it would travel 360 degrees in 60 seconds. But if you were to spin the same object at 1 radian per second, then it's going about 57.3 degrees in only 1 second.